Alrighty, good morning, guys. Can you hear me? Are there any questions or comments before we get started on the lecture? Okay, if that's not the case, then we'll get started. So where we're at is we're looking at American derivatives, and a key part in American derivative that theory is the notion of a stopping time. So we talked about it last time, and we're going to talk about it. We're going to talk about stopping times throughout today's lecture. Right? So let's recall what a stopping time is. So stopping times, the functions, you go from omega, and then you take values in the natural numbers and potentially also plus infinity. This is here for the infinite horizon model. So this is when there are infinitely many coin flips. Infinitely many periods. If there are only finitely many periods, you'll go from omega and take values in those time points, but you'll still have the possibility of being plus infinity with a positive probability. So this here is when there are n periods. Right, so n here is a natural number. Okay, so the random variable, the measurable, so they satisfy this special property. They satisfy stopping times. They satisfy that if I look at the set of omegas, right? So this is, remember, this is shorthand notation for those omegas, such that tau of omega is n. It satisfies that this set here is an Fn for all n. So it's either for all n in the natural numbers or for all n up to n, depending on which of the two cases we're in. Okay, so the most important class of stopping times is this class of stopping times that we're going to be spending quite some time dealing with this morning. They're called first passage times. First passage times. So what you do is for an adaptive process, let's write it as Mn. For an adaptive process, Mn, and a constant we define the first passage time to be this is the first time, and let me write it out in the case where we have infinite many time coins. infinitely many coin flips. So this is the first time that this stochastic process over here gets to be above k. And implicitly in this definition is that where we define tau of omega to be plus infinity if mn of omega is less than k for all time points. Okay, so on a tree, so if you're looking at a binomial model, so if you look at the binomial model, we could grow our stock price tree and so on. This here would be, say, Sn. This would be our Sn minus 1, the coin flip. If that's the case, then we could put in a k here. And so you can see there are lots of paths where the stock price, if you're looking at tau, this is then going to be the first time that the stock price is above k. You can see that there are lots of paths that the stock price it never gets to be above k. Right? So if you take tails, so you go down here, we're never going to get above k. And on those paths, tau is equal to plus infinity. Whereas if I looked at tau of, say, if it's a 3-period model, I would get heads, heads, and heads. So if I looked at something like this would be equal to what? If I have 3 heads in a row, when is the first time I get to be above this k? Well, this here is at time 0, this is at time 1, this is at time 2. Okay, so at time 2 I'm there. Whereas if I looked at tau of, say, heads and then tails, I'll go up, down, and down. I don't get to be above. And so we can also see here that tau is really a random variable. It matters what omega I put in to tau. If I put in the omega that is heads, 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 I'm going to get a 2. If I put in the omega that is heads, tails, tails, I'm going to get plus infinity. This is not constant. Are we good on so? Are we good on that? One could also extend these. One could let k be a time-dependent function. For example, you could have that k of n would be something like, it could be like e to the n. And then you would have in your tree, you will see as n grows, k gets bigger. So you could have a structure that will look like this. This here could be your k of n, right? And then you would have your tau would be the first time that your Sn would be bigger than k of n. And this here is actually what happens. This here is what happens in finite horizon American puts, which we talked about a little bit last time. And today we want to talk about the infinite horizon case. We're going to get this boundary, time-dependent boundary. Are there any questions or comments? We will also be using we'll use notation like if I have let me just continue with this Sn over there. We'll use something like this. Right, so this is going to be a random variable. Okay. How is the random variable defined? Well, it's going to be equal to Sn of omega if n is less than or equal to tau of omega. And then it's going to be equal to S tau of omega if n is bigger than tau of omega. So this process here, it reads S n min tau. Right, so it reads S n min tau. Like that symbol up here. This symbol here. This is the min. And it's referred to as the process stopped at tau. What it really should be called is, so it would be more appropriate, it should be S frozen at tau. So you'll see this symbol quite a bit. And where it comes in is in this result by Doob. So it's called Doob's optional sampling. What it says is that if Mn is a martingale and tau is a stopping time, well, then this stop process Mn min tau is again a martingale. Right, so the ingredients that go in here is you take a martingale, you take a stopping time. For example, you could take in the binomial model, you could take the discounted stock price, you know that's a martingale. You could take a passage time, could even be a dependent on time. For example, you could have right here, it could be this thing, or it could be something like k divided by 1 plus r to the nth. Right, there's nothing random here. This is just a time-dependent function. So you take a time-dependent function, you form the first time that, say, the stock price gets above, or the discounted stock price gets above. So then you have your martingale, you have a stopping time, then you can mix them by looking at the minimum. So the process, the martingale stopped at this stopping time, and it dupes optional stamping theorem says that, well, you're going to get a new martingale out of this. It also works for if Mn is a sup or super martingale, then the stop process is again a sub or super martingale. It doesn't have to be martingale. It's okay if you just have the sub with the super martingale property. It will inherit the stop process will inherit that structure. So when you work with stopping times, Dupe's optional sampling theorem, this comes in handy quite a bit. Let's do a big example. We're going to go back. We're going to work out this first passage time example in great detail for the symmetric random walk. So let's do the. So this is a big example. This is the symmetric random walk on the integers. So what you do is you start out with coin flips. So you need the size, say psi I equals 0 to infinity. Yeah, d coin flips. So psi I can either be +1, it can be -1, and it's symmetric. Symmetric here means p is equal to a half. So the IID Bernoullis, the coin flips, they come out with the two possible values are equally likely, plus minus 1. And so what you do is you to form the symmetric random walk, you take you define m, say m0 is 0, and you define mn to be mn minus 1 plus the coin flip. So this is just like what we had in the binomial model. Your process starts out at 0. It can go up, it can go down, depending on the first coin flip. So here we now have this is +1, and this is -1. You can go up to +2, back to 0, and then -2, and so on. So we have we have infinitely many coin flips. So we should feel comfortable at this point knowing that M here, this is a martingale. And it's a martingale because if I look at Mn plus 1 given Fn, I can write this here as an expectation of it will be Mn plus the coin flip. This is something that we did quite a bit around the midterm, right? We will use here that Mn is measurable with respect to Fn. Like my Fn here is going to be the coin flips. So Mn, if I get to observe the first n coin flips, get the first n coin flips. If I know what the first n coin flips is, I will know what Mn is. Mn is Fn measurable. The conditional expectation of Mn given Fn will therefore be Mn. And then the second part, the nth plus 1 coin flip is going to be independent of the previous ones. So this here just becomes the expectation. Right, but the expectation of a random variable like this one, that's going to be 0. So we have the martingale property of n. So here we have a martingale, and in particular, we can try to apply Duke's optional sampling theorem to this martingale. So we have a martingale, and we're going to look at tau is the first time. It's the first time that the symmetric random walk, right? This here is my symmetric random walk. This quantity here, this is the symmetric random walk. So tau is going to be the first time that my symmetric random walk, it starts out at 0. And let me just say that this is the first time that the symmetric random walk gets to be 1. And again, we should note that there are lots of omegas that will never reach the level 1. The symmetric random walk, I'm interested in when it crosses this level. There are lots of omegas. There are lots of omegas that would have a path that would never cross this red line here. Right, so for example, if I looked at tau on just a bunch of tails, this here would be equal to plus infinity because it never crosses on a bunch of tails. Now here my omega, there were some issues with this in the midterm, so let me try to be more explicit here. Right here, omega in little omega and big omega is a vector. Omega equals, and then it will be omega 1, omega 2. So it's an infinitely long vector with components omega n being either heads or tails. Right, so one way to write this here is to say, well, omega, this is equal to heads and tails to the power n. Like, and the way to think about this is that that is omega, and omega is a function. It's a function domain n values in HT. Is this clear to people? And so one could ask, like, how big is the set omega? So one could ask, so for example, is omega countable? Well, she says no, and can we give an argument for why that's the case? Nope. But why is it the case? Well, just think about it. If I take, so say H is 1, and say that tails is 0. Right, so then we can use that then all numbers, so all numbers x between say 0 and 1, right, can be written in terms of its 0, 1 representation. So I can write this here as a string of 0 point, and then I'll have HT, H, H, T, T, and so on. Well, what I have here on the right-hand side, this is something that I can get out from omega. Such a string here is into one-to-one relationship with something inside omega. But on the other hand, this x here, this is something between 0 and 1. Right, in the interval 0 to 1, this is not countable. Okay. So you can also look up Cantor's diagonalization if you want to find a more precise argument. But what it means is that inside this set omega we have here, this is a big set. It has uncountably many elements in it. Right, and as soon as you have uncountably many elements, but we should not expect, so we should not expect that, so we don't have, there's a don't here, so we don't have that P of omega. This is going to be equal to, like I'll write this here as a disjoint set. Right, so that's true. But this is not, so we don't have this. I cannot write this as, I cannot write it like that. And typically, indeed, whenever I look at such an infinitely long string, right, this will be probabilities of heads and tails, it's the same, so it's half times a half. What I have here, this is a 0. Right, but on the left-hand side, this is a 1. And the reason that 0 is not equal to 1 is because this middle part here, this is not true. And this equality sign here is not true because you have uncountably many elements inside omega. So this here is not true. So I'm just giving you a heads up. You look out whenever you have a space that has uncountably many elements, summing them is a bad idea because you're going to be summing uncountably many elements, and this is not going to work with measured integration theory. Okay, so that was a little sidestep, but when we're looking at our textbook, where we're playing, what we're playing is in this section 5, this random walk structure. It is bound to happen when you look at first passage times that you are on this set of omega that has uncounted many elements. So, okay. So we're then looking at, so my tau here. Hoshi is asking how we can do this. Yeah, so I'm not going to go into how to prove that you're not how to prove that the cardinality of this n here is indeed equal to the cardinality of the real numbers. There are some details to be worked out here, right? Because this representation here, this is not unique. Right, so just be a little bit careful about uniqueness, because you might have the same x on the left-hand side. You might be able to write this in 2 different ways on the right-hand side. For example, what's the difference between a half versus 0.49999 and so on? I mean, these 2 numbers, if the 9s continue, these 2 numbers are the same. And so there's a little bit about non-uniqueness of the right-hand side. So you have to argue that in theory, you would fear that maybe the right-hand side would lead to even more numbers than you have between 0 and 1, but that's not the case. This argument here shows you that you at least have uncountability, but because you might have duplicates on the right-hand side, so you have to straighten them out too. But it's not a big deal. This can be dealt with. Okay, so I want to get back on the example, because this is something that will be in your homework, and this is quite an important example. There's basically an entire chapter in the textbook that's devoted to this example here. So I want to spend some time doing it carefully. So we have our symmetric random walk, and we have the first passage time, and I pick 1 here. This is just going to be the first time that it creeps over 1. Okay. I want to figure out, so what's Tau's distribution? And I want to know like moments. So what's Tau's distribution? What's Tau's moment? And what I have is, so Doob gives us that if I take my symmetric random walk and I stop it, it gives us that the stop process, this is a martingale. Okay, so then if that's the case, then I know that the expectation, because it's a martingale, it has constant expectation over time. So I know this property. And so I can take the limit as n goes to infinity. But be careful about moving this limit inside the expectation. And so what happens is that you know that mn min tau, this process here, this is the process that is being stopped at time tau. Right, so you know that this process here, this is less than or equal to 1. Right, because tau is the first time it reaches 1. And it gets frozen at time tau. So when you get beyond tau, it's never going to move again, and up to and including time tau is less than or equal to 1. But you don't have, but there's no lower bound. It can behave arbitrarily bad from below. There's no lower bound. So you have an upper bound, but there's no lower bound. Okay, so we also recall Lec8A dominated convergence theorem. We talked about the monotone one, so there's also a dominated one. It says that for xn, so you have a sequence of random variables. For xn with the absolute value bounded by y, and y is integrable. So that's why it's called the dominated one, because y dominates. So you take a sequence of random variables, you dominate it by y, and y is integrable. We'll have, if I compute the limit of the expectations of xn, I can do that by pulling the limit inside. And the problem we're facing is that I have a nice upper bound on these m's, the symmetric random walk, but there's no lower bound. So we don't have that the absolute value of mn min tau is less than k for some k. Because the negative parts of m can be arbitrarily bad. And you can see on the picture, this here's my m, my mn is a tree. And as we move along, there's a limit to how high up m can go, but there's no limit to how bad it can be on the negative side. There's a question in the log. Does it also require? No, it does not require that. It does not require monotonicity. I mean, it requires, and you see it's provided, this is provided that it has a limit, provided that xn actually converges. So it's provided that this limit n goes to infinity of xn of omega exists. No, there's no monotonicity. The monotonicity property is replaced by this random variable y that dominates all the x's. Maybe I can show you where you can read more about this. Just find a textbook. go into the second one, and then you'll find it over here in the beginning somewhere. It's always this convergence of integrals. So this is in page 23. So we have the monotone one. This is the one that you talked about. So there you have positivity. So we leave positive. But there's also a dominated one. That's the one you have over here, the dominated convergence theorem. So now you have a sequence again. And the assumption is that your random variable y, well, here y is, you can take y to be positive, and it's integrable. Then you can do this. And then you can pull the limit inside. These are the two main theorems. So it's the monotone convergence theorem. This is the building block. We already discussed it because this is really what the foundation is. And given that, you can prove the dominated convergence theorem, and you can prove other convergence theorems too. But these are the two main ones: monotone and dominated. And we have not had the need for a dominated convergence theorem before now. And so this is why I'm introducing it now. So we don't, for M, we don't, there's no, it's badly behaved from below, it's nicely behaved from above. And so we need to get around that. And the way to get around it is by looking at a different martingale. So let me so to get around this, to get around the lack of a lower bound, we define, and it's quite unfortunate the way that the textbook has decided to call it. It's over here in that section 5, and you can see he calls this other martingale, he calls it for S, right? So it's a little bit dangerous because S is typically what we call the stock price, but there's no stock price here. Don't really know what to do about that, but maybe we could call it Zn. Yeah, let's call it Cn. And so Cn is this, so you pick a constant sigma, and then you do e to the sigma mn. Remember, m is our symmetric random walk. And then you multiply onto a coefficient, and the coefficient you multiply onto is e sigma divided by, so 2 divided by e sigma plus e minus sigma, everything to the power n. And sometimes you will see the inner part here, this inner part here. Sometimes you'll see this written as 1 over cosine hyperbolic of sigma. And so what's worth noticing is that cosine hyperbolic, so we're just going to note, we're going to note that cosine hyperbolic is positive, so it's 1 over cosine hyperbolic, this is less than or equal to 1. And if I take a sigma, so let me just pick sigmas here to be bigger than or equal to 0. And if I take a sigma that is strictly positive, I'll have cosine hyperbolics 1 over cosine hyperbolic will be strictly less than 1. So that's that coefficient, right? So I have something here that's less than or equal to 1 to the power n, and then I have this thing. So if sigma is strictly positive, this number here, right, there's nothing random about the red circle. This number here inside the red circle is strictly less than 1. So when I raise it to the power n, and I let ultimately n go to infinity, that number is going to go to 0. But that's not true if sigma is equal to 0. If sigma is equal to 0, then that number inside the red circle here is equal to 1, and 1 to the nth, that is going to converge to 1. And we're going to be playing with that in a little bit, so just keep it in mind. So the claim is, or the little lemma, it is that Zn is a martingale. And the proof is, it's not bad. It's something that we could already have done. Very similar to the proof we had that M was a martingale. We will just take a look at the conditional expectation of Cn plus 1 given Fn. And so what we do is we plug it in. E sigma Mn, and we just cosh. And now we're in this situation that we have been in many times. Need a pen that works. Now we're in this situation we've been in many times. Here we have Mn plus 1. We have n plus 1. We have Fn. Okay, so we can, this one here is not random, so you can go outside. Mn we can use, we can split it. We can split up sigma times Mn plus, and then the coin flip. And then the n plus 1 coin flip, conditional on Fn. I pull that thing outside, 2 divided by E sigma plus E to the minus sigma, n plus 1. And so this is measurable, this is independent. We'll take the measurable part out, E sigma Mn, and then the other one is independent. So we will replace the conditional expectation with the unconditional one. And then we need the factor out here, 2 divided by E sigma plus E minus sigma to the n plus 1. Okay, so we're almost there. What do we do? Well, we'll combine the E sigma Mn with the first n of the ones on the right hand side. Sigma Mn, 2 divided by E sigma plus E to the minus sigma to the power n. Then I have one left. This is 2 divided by E sigma plus E to the minus sigma times the expectation. The expectation is what? It's a symmetric Bernoulli. It's a symmetric coin flip. So this is 1/2 times E to the sigma. It's plus minus 1 plus E to the minus sigma. So we see now all the stuff on the right hand side. This combines into a 1, and I'm left with Cn. first part here, this is exactly my Cn. This part here, this is exactly 1. So this was my Cn, and this is a martingale now that it gets around some of the issues that M had. In particular, this is positive. So just note my Zn that I have up there, this is positive. I should also note that C0 is equal to 1. And we also have that as a martingale property. So just there are other applications. So maybe just note this. So these things here, this allows us to say that, well, we can actually use, Cn as a change of measure martingale. Like this is just random acronym. The random Nicodim derivative process. If we so desire, so that will be one application of this Cn, which is not what we're going to be doing today, but this is something we can do because we have a positive martingale. It starts at 1, so we can use it to change measure. What we're going to be doing is we're going to be looking at this, and now we have positivity. So we got rid of this problem from below, and let's just double check that from above we didn't mess anything up either, right? So because Mn min tau is bounded by 1, we'll have that Cn min tau, this is equal to E sigma M n min tau times 2 divided by E sigma plus E minus sigma n min tau. So on the left hand side, we have two terms, right? This one here, this is bounded by 1. So 1 to something. 1 to something is going to be bounded by 1. And this part here, sigma is positive. So you're going to get that this is less than E sigma. Right, so this is our y in the dominated convergence theorem. Right, it's a constant, and constants have finite expectations. We have my Cn, it's bounded from below by 0, and it's bounded from above by this E sigma. So we can use dominated convergence. It is this lower bound here that we didn't have for the M. It is that lower bound we now have for the C. Could we follow that? So the goal here is to use this Z here to say something about the distribution of M tau. So I have a martingale. The martingale stopped at the stopping time is uniformly bounded. So we have dominated convergence available. So now let's try to figure out what this what this thing is. So page 9. So now it's the time to make a decision on the sigma. So I'm going to make the decision now that sigma is strictly positive. So 1 over or 2 divided by e sigma plus e to the minus sigma. This is going to be strictly less than 1. So we're going to let sigma here be strictly positive. And we're going to see in a second why we need that. So what I'm interested in is going to be to stop it. So I'll look at 2 divided by e sigma plus e to the minus sigma, everything raised to the power n min tau. So what does that converge to? I want to compute the limit of this object here as n goes to infinity. Well, it depends on what tau is. So let's break it up into 2 cases. First case is when tau is plus infinity. If tau is equal to plus infinity, then n minimum plus infinity, this is going to be n. And the other one, this is going to be 2 divided by e sigma plus e to the minus sigma. This is going to be when tau is finite. And then n min tau up here. And so I'm interested in computing the limit. So we have 2 terms. This term here, this goes to 0 as n goes to infinity because sigma is strictly positive. This term here, now tau is finite. So as n goes to infinity, this is going to converge to 2 divided by e sigma plus e minus sigma. N goes to infinity, tau is finite. I'm going to get tau here. Okay. I think we have all the ingredients now to perform the calculation. So dupes, optional sampling. And dominated convergence. So to give us that z0, which is 1, this is equal to the expectation of c n min tau. And I'll take a limit. I'll write out what this expectation is. I will have e sigma m n min tau, and then this quantity here, 2 divided by e sigma e to the minus sigma n min tau. And I'm allowed to pull it inside now. I'm allowed to pull it inside now. Right, so I'm going to have two terms, right? I'm going to have something that goes to 0. And I'm going to have something that goes to this quantity. And I'm going to have a product of 2 things. I studied this part here. Now what about this part here? Well, let's have a look. How bad can this first part here be on the set when tau is equal to plus infinity? Well, when tau is equal to plus infinity, I don't necessarily have a limit I don't have a limit of mn, but I know that this quantity here is bounded. It's bounded from below by 0, and it's bounded from above by E sigma. So I have a quantity here that potentially has no limit, but it's being multiplied onto something that has a 0 limit. So if I have something, even though it doesn't have a limit, if it's uniformly bounded, when I multiply it onto something that has a 0 limit, that product has a limit 0. So the first part can be neglected when I pull the limit inside using dominated convergence. And I'm just left with the second term. So here we'll have E sigma m tau 2 divided by E sigma plus E minus sigma to the power tau times the indicator that tau is less than infinity. So maybe we should write that note out. So just note. So here we use that 0 is less than E sigma mn min tau is less than E sigma, and we use that 2 divided by E sigma plus E minus sigma to the n times the indicator when tau is equal to plus infinity, and this converted to 0. So when I take the product of something that goes to 0 and something that is bounded, that product is going to satisfy that E sigma m n min tau times 2 divided by E sigma that this also goes to 0. That means that we can forget about the first term and we can only focus on the second term. Finally, the final observation to make is, what is m tau here? When tau is less than infinity, what is m tau? What is m tau equal to when tau is finite? Look at the picture. When I reach the level, what's the value of the process at the time when I reach the level?
Is it just 1?
Yes. Very nice, Sherry. Very nice. So this here is equal to 1. Aha, so now we're getting somewhere, right? I have a mess. I have a 1 on the left-hand side. I have E sigma times this mess. So let's try to combine. So while I have the 1 is equal to E sigma times this stuff, 2 divided by E sigma plus E to the minus sigma. So it's finite. Of course, I can now, this is a constant, you can go outside. I get E to the minus sigma on the left-hand side. I get that this is equal to whatever's left in here. Okay. So I have have a formula that involves tau, and it involves tau being finite, right? So we can start getting some benefits out of all this work. One of the first benefits we can get out is this here is true whenever sigma is positive, right? We use that assumption to derive this formula, but let's try to pass sigma to 0. So then on the left-hand side, this is continuous as a function of sigma. This is going to become 1. So 1 is equal to the limit as sigma goes down to 0, the expectation of this method here. And now what do I really want to do? I have a limit outside. I really want to bring this limit inside. Do we have any bounds that we can use? I really want to move this limit inside. So I'm going to need, an upper and a lower bound on 2 divided by e sigma plus e to the minus sigma to the power tau. Is there a good upper bound for this one? It's positive. How bad can this guy get? One is the upper bound. Very nice, Roger. So I can use dominated convergence again. And what happens when I pull the limit inside? Well, sigma is going to go to 0. So I get 2 divided by 1 plus 1. 2 divided by 1 plus 1 is equal to 1. 1 to the power tau. This here is going to give me the expectation of tau, the indicator for tau being finite. Right, so here, this was dominated convergence. And of course, the expectation of indicator, this is the probability that tau is finite. Right, so that's equal to 1. Okay, so we learned something. So the probability of reaching the level 1 in finite time is 1. This also means that I can drop the indicator now, because this set here has full mass. It has probability 1. So this is equal to 1, and e to the minus sigma, this is exactly the expectation of 2 divided by e sigma plus e to the minus sigma to the power tau. So what you see in here is this looks a lot like one of these characteristic functions we have. So we can, like the left-hand side, there's nothing random about it, just this e minus sigma. And the right-hand side looks a lot like a the generating function for a random variable that takes values 0, 1, 2, and 3, and so on. Right, so this is called the generating function. This is this is alpha to the power tau. And what do we want to have here? We want to have alpha alpha between 0 and 1, I think. Yeah. So what is that equal to? And you can see, how do we get this guy from that guy? Well, we need to solve. What do we need to do? We need to solve alpha equals 2 divided by e sigma plus e to the minus sigma. We multiply over, we get alpha e sigma plus alpha e minus sigma is equal to 2. And then I can divide over by e sigma. I get alpha plus alpha e to the minus 2 sigma is equal to 2 e to the minus sigma. And this is a second degree polynomial. In e to the minus sigma. And so we can solve that. So you can solve this, and you will get e to the minus sigma is equal to 1 minus square root 1 minus alpha squared divided by alpha. And then you get the generating function. This here now becomes alpha to the power tau. The left-hand side, this is the thing you just solve for. This is 1 minus square root 1 minus alpha squared divided by alpha. And so if I have the generating function, I can compute moments. Any ideas about how to compute moments? How do I compute the moment of tau? The first one.
Why the alpha tau equals to e minus sigma.
You have a second degree polynomial.
Mm.
Like alpha plus alpha. Second degree polynomial. Like this here is, you have alpha, that's your constant, and then you have alpha times e to the minus sigma squared minus 2 e to the minus sigma. This is equal to 0. So solve this. I'm going to get a solution here. Make sure that the solution you get is positive.
Oh.
How do we use the generating function to compute moments? It's not quite the moment generating function, but maybe we can get some inspiration from the moment generating function. How would we use the moment generating function to compute moments? Taking derivatives. Okay, so let's try to compute a derivative of, say, E alpha tau. Right, so here, if we just, this is cheating, but let's do it. Right, we cannot just put derivatives inside, but if we do, what would we get? We would get tau is going to come down, and then it's going to be alpha tau minus 1. So for sure, you're saying taking derivatives, I agree. And then after we take the derivative, what do we want to do? We want to evaluate at, where do we want to evaluate? Take the derivative, and then you need to put alpha to equal something. Alpha equal to 1. Then this becomes the first moment. And what happens when you compute the derivative of this object here? Compute the derivative and evaluate it at 1. For these situations where I personally like to be lazy. And so let me just show you how I would go about doing this. I have shown some of you before, but if you're not used to using Mathematica, let me just show you. So this is Mathematica. I'm hoping everybody can see it. So if you were interested in computing this generating function, so let's call it f of alpha. This was 1 minus square root of 1 minus alpha squared and divided by alpha. I need to clear my kernel. You always have to clear your kernel when you're using Mathematica. Otherwise, it does weird things. So that's our function we had from before. And so
I can't see your screen.
You cannot see my screen?
I just see white.
Let me try to do this one more time. Why is it not sharing? My button. Okay, let me try again. Share screen. Can you see my code now?
I don't see it. I'm not sure if others also don't see it, but not on my end.
We can see your mouse, but I think the screen might be panned down, so we can't see the code.
Not happy with this. Yeah. So you cannot see my Mathematica code right now.
Oh, we can see it now on Untitled 3.
Yes, exactly. Okay. Okay, so now we're good. So this is my function up here is the one I just entered. If alpha, if I did it right, this is a function. So you're going to be doing problems of this sort in your homework, and there are going to be variations of what you're seeing now and what we've been doing today. And for example, you could move away from a symmetric random walk and you could move into a skewed walk. So we could have a probability of going up being higher than going down, and vice versa. And so what you need to do is you need to change and alter what we're doing here. And one way to get a feeling for what's going on is to use Mathematica to look at pictures for these functions. So this is the function that we were looking at. And And there was a question, for example, like how did I know that this equation we had, let me just write it out, solve, what was it, alpha plus alpha times squared minus 2 times x being 0, solve this equation, for example, for solve this equation for x, and you're going to get secondary polynomial, and this is it's this solution here then that we need. That was a question that came up, so you can quickly do this using Mathematica, right? Anyway, what I wanted to show you is how to get a feel for this thing. So you can, for example, plot. You can plot your function and the range for alpha was 0 to 1. This is how my function looks like. And what we were interested in was to compute the derivative. We were interested in computing the derivative, in particular, around 1. And so this was my function. And if I want to do the derivative, it's quite easy. I just put a prime. And you can see here, this is what the derivative looks like. It explodes. And of course, if you want, you can get a formula for the derivative. And that formula is this mess here. And you can see what the problem is. It's the first term here. When you evaluate this at alpha equal to 1, this thing here explodes to plus infinity. And that's what we're seeing on the second picture here. I just wanted to show you how to use Mathematica. It's like an easy way of getting a lot of information about the functions that you're looking at when you have something that is so explicit as what we have here. Are there any questions on either Mathematica or on what we had on the previous page? So if you go back to the document camera, you will see that this derivative, this derivative here, this on the left-hand side, the derivative explodes and alpha equal to 1. So this one here, this becomes plus infinity. Are there any questions or comments on this? So what remains outstanding here is this cheating step. So try this out yourself. Try to fill in the gap. If you can't get it to work, we can talk about in office hours. So there's a bit of cheating here because I put the derivative inside, and I cannot just do that. So can you make this step here rigorous, namely saying that if my generating function explodes, then the expectation is necessarily equal to plus infinity. And of course, if there's no moment, right? So at this point we have, at this point we'll have that the probability that tau is finite is 1, and we will have that the moment is plus infinity. And of course, this one here implies that all moments are equal to plus infinity for any k. So what I said was in your homework, you could have a skewed walk. So skewed walk, your flips, you're still going to be having the values plus and minus 1, but if it's a skewed walk, you could, for example, have, so this could be an up skewed walk. You could have P here being less than a half, and then of course you'll have Q as P is bigger than a half and Q is less than a half. Or you could have a down skewed so you go up to 1, you go down to -1. Your psi now has a smaller probability of going up and has a bigger one of going down. And so just maybe some intuition. So tau is the first time. What is the probability of tau being finite? What is the expectation of tau? If I have an upskewed, walk on the integers, tau is the first time that you reach the level 1. What would the probability of being finite be? So the picture is the same. We're still moving around in this tree, but in the upskewed walk, there's a tendency for paths to go up, right? So you're moving in this direction. Will I still reach the level K? Will I still reach the level 1? Well, we just proved that in the symmetric case, I would reach the level 1. So now I'm making it such that the walk has probability of drifting upwards to be higher than drifting downwards. And even without this, I would still reach the level 1. So it seems like this one here is still going to be 1. And what about the expectation? Well, now there's going to be mass. Pushing the walk upwards. So we're going to reach this level sooner. So maybe this is finite. If I look at the down skewed walk, what about the probability of being finite? What about the expectation? Well, I'm trying to reach the level 1, but now the path is the drift downwards. And so now this here might become strictly less than 1. And if I'm strictly less than 1 here, this is definitely going to become plus infinity. Right, so this is the intuition, and then what you're going to be asked to do in the homework is to prove these formulas. And what you need to do is to take what we just done and alter it a little bit. Going to look at a different martingale than the one we had, and then try to do a slightly different formula than what we have here. This is coming from the symmetry, and yeah. Are there any questions before we take a little break and then get back? Are there any questions on? Okay, if there are no questions, I say we take a short break and then switch the Zoom link, and then in 10 minutes or so we'll get started again. Okay, I'll see you in a bit.